Hello everyone and welcome to Digital Elevation Models and Applications course, and also welcome to the 15th lecture of this course. And this topic on which we are going to focus our discussion is one of the very popular derivative of a digital elevation model, which is based on surface hydrologic modeling, which we will see how we can use this concept of surface hydrologic modeling using a digital elevation model and can derive various derivatives or various parameters of a terrain. So, this is a very important and widely used approach to derive various parameters. When we go for this kind of surface hydrologic modeling, basically what we are simulating here is that the flow of water across a surface or overland flow of water, and this flow of water we can simulate, and while doing this we derive lot of derivatives from a digital elevation model. One assumption which we will be discussing also, that here we choose this surface as a completely insulated surface, and that means that whatever the water which will come in form of rain over the terrain has to flow on the surface. So, remember this assumption, we may discuss again in later part when it comes there also. So, basically to model the flow of water across a surface, and also as you know that the shape and characteristics of the earth surface is useful in many fields of study, and there this plays very important role, that is the surface hydrologic modeling. And also it is important to know that how these things are changing a composition of a area and how it affects the flow of water. And what happens, because we want to simulate the conditions, and that what happens when deforestation occurs or what happens when afforestation is done to the water flow or to the soil moisture conditions. So, these things can also be modeled using our surface hydrologic modeling models and based on DEMs, and how this can affect at a watershed level, catchment level or a basin level. That can be, because these are the hydrological boundaries, the watershed, catchment or basin, and therefore generally whenever we work for a problem which is related with hydrology, then we have to look for natural boundaries rather than political boundaries. And also how we can mitigate a problem, maybe a soil erosion problem, maybe a flood problem or so on. So, these can also be there also we can use these approaches, that is surface hydrologic modeling. There are various applications, some of which we will be seeing in this discussion. So, first before we proceed for typical surface hydrologic modeling steps, which is a sequential processing, we would like to understand first what is basically drainage system is. So, this is the area upon which water falls in like a watershed boundary, and the network through which it will travel to an outlet is referred as a drainage system. So, there is a network of drain lines starting from first order stream to second order, third order, depending on the size of the basin or watershed, and the water which will come as an input as a form of rainfall or precipitation has to flow through this network. So, where it will flow, exactly how it will follow, this will depend on elevations, and that is why elevation models are used along for in surface hydrology modeling to drive drainage network as well. And the flow of water through a drainage system is only a subset of what is commonly referred to as a hydrologic cycle. And because a hydrologic cycle encompasses the complete flow of water or movement of water through all processes, but this drainage system, the flow of water in a drainage system is just a small part, and which the hydrologic cycle includes precipitation, evapotranspiration, and groundwater flow. Whereas directly in surface hydrologic modeling, we cannot handle like evapotranspiration issues or outputs or groundwater flow as well. So, but overall this hydrologic cycle will include all these. Surface hydrologic modeling, that is why name says it only take care about the water which is flowing on the surface of a terrain on an area, and assumption is that every drop of water will flow over as a surface runoff. So, this has to be remembered here. So, surface modeling focuses basically on the movement of water across a surface over land flow or surface runoff, which we talk. So, here we are having a drainage basin, or a large one is there, a watershed boundary is also there, and in this schematic we are also having a drainage network, and this is the outlet, or also called pour point. So, for a larger basin, the pour point is going to be here. For a smaller watershed or a sub basin, it may pour point may be in the upstream area. And these are the boundaries which we call as hydrological boundary rather than political boundary. These hydrological boundaries are based on elevations, and this is what the surface hydrologic modeling exploits. Basically, because water will also flow through low elevation areas surrounding, maybe you may be having higher areas, but water will flow through always the low elevation areas and to further low elevation areas, and therefore it will create a track, and this is that we call as a drainage network. So, the drainage basin is an area that drains water and other substances to a common outlet. These substances may be sediments, maybe nowadays pollutants or other things as well. So, whatever is will flow through this in this drainage basin at that particular outlet where we are deciding that this is going to be our outlet. In this surface hydrologic modeling, a user can choose interactively where he is going to choose the outlet, and accordingly a watershed boundary will be delineated. There are other terms which are used for drainage basins, for example, like watershed basin, a catchment, or a contributing area. And opposite to this is a distributing areas, which in civil engineering or in hydrology it is called command area for a canal network or some other thing. So, that is just opposite to our drainage basin or watershed boundary or watershed basin. And this area is basically normally defined as the total area flow to a given outlet of a pour point. So, the outlet is very important, where we are choosing the outlet. If we shift the outlet at say this location, then we may have a watershed of this much size. But if we go downstream for the choosing the outlet, our basin or watershed will become larger and larger. So, this has to remember, the pour point is the point at which water flows out of a watershed. So, again, as we have discussed, that pour point from where the water will come or whatever the sediments and other things will come. And this is usually the lowest elevation point of along the boundary of a drainage basin. May not be exactly within lowest point within the watershed, but at the boundary of a drainage basin or watershed boundary, and between two boundaries or between boundaries of two basins, it is referred as a watershed divide or watershed boundary as well. So, because topographically it makes basically a ridge, and that ridge will not allow water, will allow water to flow either in one basin or one watershed or another one. So, that ridge serves as a divide, and therefore, sometimes people call as drainage divide. or that also becomes watershed boundary or basin boundary. Now the network through which the water will travel to the outlet, which is in this schematic, it is shown as a red points as either is a large one or a smaller one, and this network can be visualized as a tree with the base at the tree being at the outlet. And there are though patterns are there, but we will discuss little later. And the branches of these trees are basically these are the stream channels, or these are the drainage lines are there, and the intersection of two stream channels is referred to as a node or junction. So if we talk in terms of vector data, and the same concept is used when two vector lines meets, then we say node, or maybe internode and other terms can be used. Similarly here, that the intersection of two stream channels is referred as a node, and the sections of a stream channel connecting two successive junctions or a junction and the outlet are referred as the stream links. So these are important while doing surface hydrologic modeling. Now here, traditionally what we have been doing in order to drive the watershed boundary, we used to have a topographic maps, and in which based on the contours we used to drive or delineate a watershed boundary. And this is once we decide the outlet, suppose outlet is decided at this location, then delineation will start following the contours which are making the ridge, and likewise a watershed boundary can be delineated. So traditionally this is how manually this was being done, that we sketch throughout this thing following the watershed boundary. But on a GIS platform, using a digital elevation model and employing surface hydrologic modeling, we can delineate watershed boundary at any location within our digital elevation model, and it is after certain steps of processing, it can automatically be delineated if we decide and the size of basins. So if we say that I want to delineate all watersheds which are having 500 area equal to 500 square kilometer or more, then through surface hydrologic modeling this can be done automatically for a large area, whereas in a manual method for individual watershed boundaries have to be delineated. Now we will go through one by one about this surface hydrologic modeling processes which are there. As I have mentioned, most of the processes are in a sequence. So we will go one by one. Like first, generally what we do, we take a digital elevation model and drive directly flow direction. And again, using the same digital elevation model, we can find out where are the sinks or artifacts in a digital elevation model, because digital elevation models may have some errors. And why these sinks are identified, or depressions, local depressions of one cell size or maybe 2 cell size sinks are or depressions are identified, because water has to flow on the surface. It cannot remain intact or remain on one place, because this is what in surface hydrologic modeling is. It is delineating, or it is basically assuming that water has to flow on the surface as surface runoff, and therefore these sinks have to be identified, and later these sinks, if they are there, these have to be filled. And once you have filled, and then you are having a depression-less digital elevation model. One output we have already created a flow direction, and then we are having a depression-less DM. So these two outputs will allow us to create one more layer or theme, which is flow accumulation. And once we reach to this stage, which is a very simple, very quickly one can perform and can reach to these 3 products, that is flow direction, depressionless DM. This depressionless DM and flow direction goes to calculate the flow accumulation. This flow accumulation can be used to calculate stream order, stream and links and other things are there. It can also be used to calculate flow length, and that pour point or a snap pour point, and ultimately all these processes will lead to delineate the watershed boundary. For an entire area in one go, depending on the size which we declare, or we can choose a pour point or location of a pour point, and as soon as we click, then automatically the watershed boundary is delineated. This I will be showing through few slides. And basically the most common digital data of the shape of the Earth's surface, as we know, is the DEMs, and these DEMs we used, and the data is this DEM as a input, basically which quantify the characteristics of the land surface and surface hydrologic modeling. Further, the accuracy of DEM is determined primarily by the resolution. So, higher always for this kind of processing, a better or higher spatial resolution DEM would give us the better results, and the factors which basically affect the accuracy are the data type, that is the cell values of a digital elevation model, whether we are having integer value or real or floating point value, they will influence sometimes our results, but generally in a digital elevation model we are having real values or floating point values, and actual sampling of surface where this surface hydrologic model will be performed of a original digital elevation model. So, these things will influence our surface hydrologic modeling outputs. As you know, the errors in DEMs are usually, as mentioned, can be classified as sinks, depressions, or maybe peaks, but for a very small area, not very, maybe one cell size, two cell size, not more than that. So, we consider them as sinks, and we identify them in the very first few steps, and then fill those sinks using the surrounding values, so that the water can flow throughout the drainage system. So, sink, as I have said, that is a higher area surrounded by higher elevation values, or in case of depression, or in a peak it may be a lower elevation values. And this is the area of internal drainage, because here the surface runoff has to be there, and therefore these have to be filled. And when we are having this digital elevation model which is depressionless, sink filled, then it is ready for surface hydrologic modeling. And these are more these sinks are more commonly natural features, maybe sometimes depending on the terrain, and of course terrain ruggedness plays very important role, but nonetheless these will be used while calculating the flow direction. So, that is why in the flow chart flow direction has been calculated first, but sometimes people first go for depressionless, creating a depressionless DEM, and then drive the other parameters. That is also possible. So, these have to be removed, or these have to be filled with surrounding values, and once it is done, then we assume that now water will flow over land or as a surface runoff. And this is one example of sinks here, that there are five cells which are having values lower than the surrounding. So, we can we can fill, so that this depression is removed. But generally, through my own experience, I have seen the sinks are of not that much size. They are generally of just 1 or 2 pixels maximum. And as said, that the sink are the areas of internal drainage, and we have to get rid of these internal drainage to allow water to flow over the surface. And these sinks can occur when all neighboring cells are higher than processing cell, or maybe lower in case of a peak in a digital elevation model, but this peak is just 1 or 2 cell size. So, number of sinks in a DM is normally higher for coarser resolution DMs, because coarser resolution DMs may have more errors in form of sinks as compared to relatively higher spatial resolution. And now instead of 90 meter spatial resolution, which we used to call as a coarser resolution, most of us have started using 30 meter or higher spatial resolution. So, this issue of sinks have become little less or less problematic in our surface hydrology modeling. Another cause of this sinks results from storing the elevation data as an integer number. So, by mistake, if data has been stored, then because integer numbers will not allow the values, at least one least count will be there, and that is why it may create some sinks. So, generally, as I have mentioned already, that the digital elevation cell values are generally stored as a real values rather than integer values. So, this care has to be taken before we put a DM through this surface hydrology modeling. And as we know that these things can be avoided once we get a digital elevation model of our area of interest. First we should study visually, otherwise look the minimum values, maximum values, and the cell values, whether they are integer and real. Once that is done, then we can proceed for surface hydrologic modeling. So, depending on the spatial resolution, as in this example, as that increases as much as 5% for a 3 arc second DM, that means 90 meter resolution DM. The example is here that the same digital elevation model which we have been using throughout this course, the subset of that DM is shown on the left side, and when this DM was subjected to sinks or sinks identification, this is how these number of sinks have been identified. Only 186 cells which have been found having values lower than the surrounding values, or values having very significant higher values. So, generally these are the local depressions which we need to remove or fill, and once that is done, then we can proceed for next step of surface hydrologic modeling. Now, so this analysis or surface hydrologic modeling basically is designed, the concept is based on this, the convergence of flow across a natural terrain surface. This has to remember that the water has to flow over the surface, and this assumption, as I have been mentioning, that this assumption basically is that the surface contains sufficient vertical relief that a flow path can be determined. So, you have to have a sufficient change in elevation, and therefore, the water can flow. And the tools which we use in different GIS platforms, they operate on this assumption that any single cell, the water can flow in from many adjacent cells, but through only one cell. So, there may be various cells may be having lower value elevation values, but it will flow through only that cell, a single cell which is having among the surrounding cells the minimum elevation values. And when we delineate these watersheds or defining a stream network, we proceed through a series of steps as shown through the flow chart. Some steps are required, some other are optional depending on the characteristics of input data, and also depending on what we are going to achieve through this surface hydrologic modeling, because somebody may be looking only up to drainage network and not looking for stream ordering, or may not be looking for watershed boundary. So, depending on that we go for steps. Flow across a surface will always be in the steepest downslope direction. This we know is a very simple fundamental thing, is the basic thing. Once the direction of flow, that is why the first step here is to calculate the flow direction. So, once the direction of flow out of each cell is known, it is now possible to determine which and how many cells flow into that given cell, and that will decide the flow accumulation. So, the first after depression or even before that, the flow direction has to be calculated. So, both approaches are available based on the depressionless or on the original DEM. The flow direction can be calculated, but for flow accumulation a depressionless DEM has to be there. And the information can be used to define watershed boundaries and stream networks, that is the flow accumulation information. And the chart which I am going to show are having this information, watershed boundary, stream networks from a digital elevation models, and we start with always whatever is the ultimate aim or ultimate derivative which we are targeting, we have to start always with the digital elevation model, and this is based on in which cell the water will flow from which cell, and this will decide basically the direction. So, this is a repeat flow direction that flow chart which is here, that we will, after having a depressionless DEM, then a flow accumulation theme is calculated. This theme, as mentioned, can be used to derive a stream network, stream order, or stream to features, means from raster to vector here, or a stream link files which can be used later on in case of watershed boundary delineation, and other in between parameters can also be derived. So, like driving runoff characteristics of a DEM of a terrain through a surface hydrologic modeling. So, the error part we have already discussed, that if there are errors in digital elevation model, or if you are modeling a karst geology, that means the terrain which is representing a limestone terrain, and there we are having these limestone related rocks, and then one has to take care, because we may have a large sinks there. Otherwise, generally we do not have this problem. And so, because you may have these lower areas, and generally in this karst topography or karst geology, we do not have this in calcareous terrain, we do not have surface drainage. So, only subsurface drainage network is there, but it is a very not a common phenomena, and if this is the situation, then probably the surface hydrologic modeling will not work. But otherwise, in most of the cases there should not be any problem about this. So, when we go for depression, remove the depressions or depressionless elevation model, then we can also later on drive the flow direction, flow accumulation, and so on and so forth. While delineating watershed boundaries, first 4 points need to be identified, that we have already discussed. Then these locations are mouths of streams or other hydrologic points of interest, such as gauging stations, and in surface hydrologic modeling we specify 4 points while delineating a watershed boundary, and one can use the size of give a threshold, that if 500 and cells or 5000 cells or a square meter area is contributing, then I want to delineate. So, likewise the drainage network and everything can be determined, and this to create the watershed for each stream segment between stream junction. So, stream link information is also becomes very important. Once the drainage network has been derived, then we can use for other things. So, in order to create a drainage network after the flow direction, the next thing is flow accumulation for each cell is calculated. If we look on the cell basis how flow direction, the one major theme which we drive is on the left side, top left, basically we are having a elevation digital elevation model of a very small area is shown here, and when we create a flow direction we follow a scheme. Generally this is the scheme for coding, and so these are not basically elevation values, these are the codes of flow direction. So when a cell is allowing water to flow towards the east, then the code 1 is given. When it is going for southeast direction, then code 2. Likewise, when it is going for north direction, then code 64 is assigned, and if it is going for northeast direction, then 128. So it is in a particular digital elevation model. It may not be necessary that all codes will be used. Same thing here in this example, there are few codes like in the 64 code, 32 code, and these codes have not been used, whereas the code 1, 2, 4 and 128, 16 have been used. That means the flow in these directions within this example DEM are there, but in other directions like in north direction, northwest direction, there is no flow is there. So it is not necessary that all codes within a given or a DEM will be given these all codes. There it depends on in which direction the flow is going to flow from, water is going to flow from one cell to another cell. So flow direction conclusively a definite line or course in which something is issuing or moving in a stream. And when we see in a form of the same digital elevation model and a really large file instead of just on cell based as we have been seeing in previous slide. Here this is the DEM which we have taken an example DEM throughout this course, and the flow direction has been determined. Sometimes one may feel the flow direction looks more close to slope map. In fact, yes, in some way, but basically the codes have to be taken care, because the codes there are different than here, otherwise the output may look similar in that sense. But we cannot equate directly. So codes have to be taken care, because these codes are later on used while calculating flow accumulation. So this flow accumulation map is here. So this is showing the major drainage, and of course if I on a GIS platform, if I click directly say here, then automatically a watershed boundary will be delineated. So this flow accumulation, flow direction and flow accumulation generated using a field DEM in this particular example. Now how to identify stream network? For a stream network, the theme which will go as an input is of course the flow accumulation theme, and here it is that we have to define a threshold value, that how many cells will contribute for a outlet, and based on that the stream network will be driven. So flow accumulation in its simplest form is the number of upslope cells that flow into each cell. So if I take example here, here these at this location the maximum number of cells will contribute at this location. But if I go here, then relatively I will have less number of cells which will be contributing at this point. So this is what it is meaning, is that the flow accumulation in a simplest form is the number of upslope cells that flow into each cell, and therefore the values will be also accordingly. So at higher elevations, say near watershed boundary, you will have a very small flow accumulation value, whereas at pore point or at the, in this particular example, at the edge of our watershed from where the water will go out of my study area, the flow accumulation value is going to be very high. because it is declaring the upslope cells which are going to flow into each cell. And by applying this a threshold value to a flow accumulation theme, a stream network can be delineated. And likewise, I will just show you that for example, if I to create a raster where value 1 represents a stream network on a background of no data, the two's parameter could be as follows, that for example, I can decide that the threshold value is more than equal to say 100 cells. That means that if 100 cells or more are contributing, then start delineating drainage network from there itself, because I cannot have each cell. If I go and reduce this value, then too dense drainage network will be delineated, which will not be close to natural drainage network which we see on the ground or through a topographic map. So this threshold value has to be judiciously chosen, so that at least some comparison can be made. Here flow accumulation is there, and what we are seeing here, the drainage network in form of blue lines, and in the background a hillside has been put here just to show that how if this becomes the watershed boundary, and at this outlet as you can see, and the drainage is just going through here. Likewise, if I have chosen a very small value as threshold value, then too much drainage lines would have been delineated, and though the system will calculate, but they may not be close to realistic, means you will not see on the ground really, or on even on a large scale topographic maps. So it is always one has to be careful while choosing the threshold value. So here in this particular example, the threshold value was equal to or greater than 100 cells. So once we choose or one may go for, instead of number of cells, one may decide based on the area, and accordingly it has to be given. Once the stream network is created, it is further analyzed for stream order or stream links. So as I mentioned in the beginning, that it's a sequential processing. We started with digital elevation model, we filled the depressions, we calculated the flow direction, we calculated, then using the flow direction we calculated the flow accumulation. Once the flow accumulation is there, we apply a threshold value and calculate it and determine the drainage network. Now once drainage network is there, then this we can use to drive two products. One is stream order and stream links. Stream links is used later on, but stream order, there are different stream schemes which exist. The most popular one are the SREEB given by a scientist or geomorphologist, SREEB and Streller. So these two stream ordering schemes have been implemented into GIS softwares and within this surface hydrologic modeling, and there are slight changes in this. We will see the differences in this, that in this Streller, let's take the later one first. So Streller stream order only increases when streams of the same order intersect. What does it mean? That when I am having order 1, first order stream, when these two meets, then it becomes second order. When second order and first order and these meets, then still it remains second order. So once we are having two second order streams, then only it becomes the third order. This is Streller scheme of ordering, stream ordering. Now if we go for this first, the SREEB, when two links intersect, their magnitudes are added and assigned to the downslope link. It is a kind of addition. Example here for the same schematic drainage network, that first order meets, it becomes second order. When second order and first order meet, it becomes third order in the downslope side. When this happens, first order and third order meets, it becomes fourth order. When third order and fourth order meets, it becomes seventh order. So in SREEB ordering, what we are seeing that at the outlet we are having a 7th order, whereas in case of stellar it is just 3rd order, though the drainage network is same because of two different way of ordering streams are there. So, both options generally have been implemented in popular GIS softwares. Depending on our requirement we can choose, but this one becomes more sleeve one becomes very easily understandable, and it is therefore very much popular. Now, stream and there are other stream ordering schemes are available in literature. Some of them have also been implemented on GIS. So, 5 popular one are shown here. 2 we have already seen, stellar and stream ordering. Then there is a Horton stream ordering scheme, there is a Heck stream ordering scheme, and there is a topological stream ordering scheme. Different schemes are there. One can follow any one or the most popular one, which is the Shreve one, and these are the 2 which are most popular. Now, if I take our example digital elevation model on which we have generated our this flow direction and then later flow accumulation and then stream network. Once we put this stream network for this stellar order stream, then this is what the output we get for our example digital elevation model, and if it is subjected for a Shreve order, then this is how it looks. Though the drainage network, overall drainage network is the same, but when we apply 2 different stream ordering schemes, then we get slightly different results here. So, depending on your requirements, one can choose any one of these ordering streams. So, this brings to the end of this discussion. The surface hydrologic modeling is in 2 parts. The first part we have discussed. In next lecture we will be discussing the second part of surface hydrologic modeling. So, we will be discussing few more derivatives which will be coming through surface hydrologic modeling using a digital elevation model. So, thank you very much.